get back to business after lunch. Right, so my aim with this talk is basically to try to give you guys sort of the background, some physical pictures, and a bit of technical tools that will, should help you follow what's going on in the field of periodically driven quantum systems. It's a big field. There's much activity in many directions right now. So I'm not going to focus on the cutting edge of research at this point. I think since this is the tutorial, the idea is to really focus on background, develop the ideas, and then after this, I should be able to go on and follow the literature. So it's really in the spirit of the school that I'm going to give this talk. Right. So just to begin, what's the motivation? So why are we talking about periodic driving at all? So there are a few reasons why periodic driving is an interesting subject. One is that periodic driving is a tool that can be used for probing quantum systems. So in the spirit of, say, spectroscopy, right? We have some system, an atom, maybe it's some kind of spin in a magnetic field, and we apply some radiation and can look for resonances when the frequency matches energy splitting, and thereby learn something about the spectrum of the system. Okay, so that's the way that periodic driving has long been used as a tool for probing quantum systems. Additionally, periodic driving can be a tool for controlling quantum systems, not just for finding out what's there, but for getting some new behavior to come out of the system that it wouldn't have done naturally in equilibrium. So here's sort of just one particular direction that comes from my own personal interest, is that this type of quantum control could be used, say, take some material. In the past, hundreds of years ago, we had alchemists. Right? They had some materials that they weren't so happy with, lead, and hoped that somehow they could get gold out of it. And we know that it didn't work that well, but at least lots of chemistry came out. So now, today, we might say, well, we have some material, we like it, but maybe there's some even more exotic material that had some different properties. Can we somehow coax this sort of more simple material into displaying this more interesting quantum behavior by driving it, say, with lasers, like this? Okay, so that's one application of this kind of idea of quantum control, one particular. So really in this talk, I think the theme will be more aimed towards this idea of controlling quantum systems, because now it's 21st century, and I think that's really where the field is going. So we want to understand driving from the point of view of how can we understand the dynamics induced in a quantum system by driving it, and what can we do with it. Right. So here's the basic plan. In the beginning, I want to just sort of start us all off on the same foot and develop some physical pictures and some intuition based really on two-level system. The two-level system, it's really the simplest, non-trivial quantum system that there is. But despite the fact that it's so simple, we can learn a lot from it and develop a lot of intuition, which can be important to more complicated systems. So we'll spend some time just reviewing two-level systems and applying certain ideas there that we can then use in more complicated systems later. Then in the second part of the talk, we'll give a little bit more introduction to some technical machinery that's quite useful in the end for studying periodically driven systems in a sort of beyond the simplest possible regime of just a simple rotating field. And then finally, I guess this is a little bit more specific than I'll do in the end, I'll talk about some applications where ideas of periodic driving can be used to do something non-trivial. Right. So part one, let me just begin by recalling to mind about two-level systems. So first of all, why two-level systems? Well, two-level systems are all over the place in one form or another. So there are many different types of physical devices or systems where similar behavior can be achieved, similar from the point of view of a theoretical description we may use for it. Okay, so here are some different situations that we may describe as a two-level system. For example, a superconducting circuit forms a qubit. Here, we may have clockwise and counterclockwise circulating currents that would correspond to two different quantum states. Or say a spin in a quantum dot that has two states, spin in a nucleus of an atom. Also, if we have a particle in a double well potential, say it's a double quantum dot, I just have an electron that can tunnel back and forth. all of these different physical systems, in some way, basically, you know, if we focus on low energy states, have two quantum states that they can be in, or that form a basis for the Hilbert space. And therefore, by studying two-level systems in general, we'll actually be learning something about all of these different systems at the same time. Right? And so actually, there's one sort of unifying picture that I like to use to think about this, which is, there's one particular type of two-level system that probably we learned about first in our studies, which is a spin 1/2 spin, right? That has two states in its Hilbert space. And so actually any of these different physical systems that I want to describe, once I restrict to the two lowest levels, I can think of by mapping it into some kind of spin picture. And that's useful because spins are very geometrical. We can picture them, we can imagine how they rotate, and that helps us develop some intuition. Right, so just to take an example, suppose I have a two-level atom with some kind of ground and excited state, and maybe there's some perturbation that's coupling them. So this Hamiltonian, it's very abstract. It's just a bunch of symbols on the page, some cats and bras. But if we now define Pauli operators in terms of these states, so sigma z would be, you know, difference of projectors onto excited and ground states, and so forth, then this Hamiltonian, which didn't have any particular geometric meaning, suddenly can be expressed essentially as some kind of spin in an effective magnetic field. And now there's some geometry in the problem that we can use to visualize. But let me say a couple of things that I should have said at the beginning. First of all, please stop me at any time and ask questions. It's much better if we stay together the whole time than waiting to the end to undo any confusion. And the second is a warning that I realized just before the talk. There are some inconsistencies with minus signs that will appear. Some convention may switch in the middle. So if you're bothered, just ask and we can resolve it. And I apologize for that. But I didn't have enough time to fix it after I caught it. Okay? So, but the basic idea here, right? So we start with this Hamiltonian. Now we've written it as some kind of effective spin in a magnetic field. And so one thing that this gains is now in this picture you'll never ever again diagonalize a Hermitian 2x2 matrix by solving a characteristic equation. Because you'll just take this 2x2 matrix and you'll see that, well, that corresponds to some magnetic field which points in a particular direction in three-dimensional space. And then remember that the eigenstates of a spin in a magnetic field point along and against that field. And such states are the coherent states of a spin. Right? So the coherent state of a spin has maximal projection along the direction of some unit vector n. Okay? And there's this simple formula, all you have to do is remember that, where theta and phi are the polar azimuthal angles in spherical coordinates. And as soon as you remember this, you already have your eigenstates. You're done. You just have to solve some triangle. Where is it? Oops. Here. So we know that here is our vector. I just have to find out what are the angles that correspond to this field in spherical coordinates, and I'm done. And the energy, the eigenvalue of this thing, is just the length of that vector. Right, so this thing. Good, okay, so now in terms of dynamics, also we understand how spins evolve in the presence of a static field. So if I have, here's a Hamiltonian, minus v dot s, the equation of motion for the spin is just the Bloch equation, v cross s, which describes Larmor precession. So if the spin is not initialized exactly along the field, but at some angle to it, it'll precess with its projection along the field constant as a function of time. So throughout the talk, there'll be a few points where I put this word exercise here, which is basically to tell you if this isn't something that's familiar to you, or you don't remember how to derive it, you should go home and do this afterwards. Okay, so take a picture of it or write it down on your page. These are all things that you should know, and if you don't, then it's a good thing to practice.
Aren't you missing something in this equation though? Because like it is now b is 1 per second.
B is what?
B is 1 per second.
You're talking about units.
Yeah.
There okay, so there should be, in principle there should be some magnetic moments here and some h bars, and they're all 1. But yes, good. So in your exercise, you can fill in all the units as well. Thanks. Right. Okay, so this was about a spin. Now, as I said a minute ago, that this effective spin language was useful for learning something about all kinds of different physical systems. So now if we come back and say, let's think about tunneling, say, of a particle between two quantum dots. So this double well potential represents potential energy landscape of a double dot. And now I want to understand what's the dynamics like. Suppose I initialize an electron in the left dot, and I have some energy detuning of the two sides, and a tunnel coupling J. What's going to happen? You can understand this by thinking back to this procession in some way. So your second exercise to think about would be, try to sketch what would the probability look like to have the particle in the left well as a function of time. And you can do it just by thinking about this picture we had a second ago. Right, so that's another thing we're not going to do, but you can think about it. Okay, so this was very simple basics. Now, if we want to do quantum control, which is something that I mentioned was a goal at the beginning, that's not very interesting. So from this point of view, here, this procession we discussed, there's a projection of the spin along the field, this vector field, which is conserved as a function of time. So if, for example, I wanted to make this spin go somewhere else, where that projection would change, I won't be able to do it by using a static field. But clearly I need some kind of more complicated, time-dependent fields if I want to exhibit some kind of non-trivial evolution of my quantum state. So that will force us to now look into time-dependent Hamiltonians, not just static ones. And one object that plays a key role in all of this is the time evolution operator, which is just time-ordered exponential of integral of the Hamiltonian. So this is where you get, normally it's just exponential of h. If h doesn't depend on time, if it depends on time, you need a time order. Good. Okay, so the simplest case that we can imagine that gives us, in fact, full quantum control over a two-level system, and by full control I mean that any initial state can eventually be brought to any final state, is if I just apply two different Hamiltonians, say h1 and h2, I call them, statically, I apply one for some amount of time t1 and the other one for time t2, then this composite evolution can get me from any place to any other one. So this is a useful place to start thinking about time-dependence, time-dependent drive.
Sorry.
Yes.
On the previous slide, that equation, is this the equation for potential we must find, is this an integral equation? Because I don't know if this potential is already a part of H or it is another addition we need to look at.
Which potential? Sorry, which potential?
The question was whether U is a potential.
No, that's a time evolution operator. It's a unitary operator. It's clear? Yeah. Okay. Right. Okay. So everything called capital U will be an evolution operator throughout the talk.
Yeah.
Right. Okay. So here's evolution. So suppose we take as an example this. To get rid of units, h1 always multiplied by t1. This will be some angle, theta 1, and then there's some direction, unit vector n1 that describes sort of the, whatever these couplings are that are in the Hamiltonian, and a different one where n2 is not parallel to n1. So this gives me two different rotation axes I can think about. Then this time evolution will be the product of those two rotations. Now, there's actually two super useful formulas, and these will be useful at the very end of the talk for actually your final homework assignment that you'll get, that we should all remember. And if we don't know them, we can learn them now and then remember them. So the first one is how to evaluate exponential of polymatrices. So that's this formula here. I don't think any explanation is needed, it's just a formula. And the second is what happens when I multiply polymatrices like this. I didn't say it was an exercise, but actually if this formula isn't clear, you should also derive it. It just follows straight from commutation relations of polymer, anti-commutation relations of polymatrices. So you can derive it. But having these two things, then actually we can simplify. See, this evolution is still complicated. I have two matrix exponentials. I have to multiply them together. But now, using these formulas, I can combine them into one rotation about some axis t and some angle theta t, which you can find. Actually, here is your exercise. Now, real one. You can find that angle and that unit vector using those formulas. Right? So now I've taken this composite evolution and mapped it to a single rotation, which gives me the same final state that I would get by these two rotations. So that's sort of the simplest version of some time-dependent Hamiltonian, and this one I can actually solve. Exactly. So it's kind of useful from that point of view, and actually it's a common device that's used theoretically, if I want to talk about a driven system, is to apply sort of stroboscopically different constant Hamiltonians, because often that's something that can be solved, whereas a generic continuously varying Hamiltonian, there's not much we can do, because this time-ordered exponential generically can't be evaluated. Right? So it's kind of useful to think about this alternating between different Hamiltonians. Okay, so there's one other case, maybe exactly one, maybe there's one or two others, but one other case that I'll talk about now, which can be solved exactly, and that's the case of a rotating field. Okay, so now this is the first case of a periodic driving that I'll mention. So here, my Hamiltonian, I have some energy splitting which sits on the diagonal, and now on the off diagonal we have some complex exponential, which indicates, if I translate again back to the spin language, that I have an effective magnetic field, the static part, for z, and then a transverse part, which is rotating in the xy plane, as shown in the figure. Right, so x component, y component, they're 90 degrees out of phase. So it's a field which is just rotating around. Right, so, I mean, as you can kind of see from the geometry of this problem, since everything is rotating, it might be useful to jump into a rotating frame and then see if the problem is simpler there. So that's exactly what we'll do. Now, technically, the way to do it, which is again this very useful trick which happens over and over again, so it's a good thing to have, ready at your fingertips, is make unitary transformation like so. So psi r means the quantum state in the rotating frame, and that's related to the state in the lab frame by this time-dependent unitary transformation. And remember that the spin operators are generators of rotations. Right, so here I have sigma z, actually 1/2 sigma z is sz. So this is an operator which rotates spin around the z-axis by an angle omega t. And that way I can just undo this rotation of the field. Now, what I want is the Schrodinger equation for the state in the rotating frame. So to get that, I should just take the time derivative of psi r and use chain rule twice. Use chain rule once. I get two terms. First, I take the derivative here, it pulls down this omega sigma z, and the second piece, time derivative x on psi, and that's just h psi, that's the original Schrodinger equation. So this thing, if I multiply by exponential and its inverse, I can express the whole equation in terms of psi r, and now I have whatever this new Hamiltonian is that acts in my rotating frame. It just consists of these two pieces, the transformed Hamiltonian, original Hamiltonian, and one piece which came from the derivative of the transformation itself. Okay, so the key feature is that for this problem of a rotating field, in the rotating frame, this Hamiltonian HR doesn't depend on time anymore. And then it becomes a simple problem, because we know how to solve problems where the Hamiltonian doesn't depend on time. That's what we spend, all of our education learning how to do it. So, first of all, what do these two terms do? The first one, which is proportional to sigma z, it essentially modifies the diagonal. I had original splitting epsilon, now it's going to be epsilon minus omega. And I call that thing delta epsilon here. And then over here, it's just a little bit of algebra of what happens with these polymatrices, but you can just multiply them out. It's a very simple calculation. And you'll see that when I sandwich, say, sigma plus by the transformation, I get e to the I omega t sigma plus. And if I come back here, this is my sigma plus term. There was already an e to the minus I omega t, it'll cancel, and so I just get constant v sitting there. here is my Hamiltonian in the rotating frame. And in the geometrical picture of this whole thing, that just corresponds to some effective field, which is now in the xz plane. And the z component, instead of being epsilon, the original one, is this reduced splitting, this detuning, and then the driving strength, v, is the x component. All good? Okay, so now we can understand the phenomenon of Rabi oscillations, which hopefully is familiar in this picture. So in the lab frame, remember, I had a big splitting. Now if I drive with a frequency which is not very close to that one, then in the rotating frame I still have a big splitting. And my effective field mostly points to the z-axis. And so what this looks like here, did I use this picture already? Anyway, yeah, so here I have this sphere where I plot the coherent states. So I would see that if I start, say, in the excited state, and I let the system evolve in the rotating frame, it'll just process around this tilted field, but it'll stay near the North Pole all the time because this effective field is also close to the North Pole. So here I get these oscillations. They're rapid, but with small amplitude. Now when I drive very close to the resonance, what happens is my detuning, this delta epsilon, is close to 0. If it was exactly on resonance, it would be 0. And then the field that I see in the rotating frame is actually dominated by the driving part, the v. So it mostly points along the x-axis here. And the splitting in the rotating frame is in fact dominated again by the driving field, or sort of more exactly, the splitting that I see is the length of that vector, which includes both the detuning part and the driving field part. And for small delta epsilon, this thing is close to just being v. Now the other important feature is that since this field points close to the x-axis, if I start near the North Pole, this Larmor precession in the rotating frame will take me almost exactly to the South Pole. And if I was exactly on resonance, I would go exactly to the South Pole. So this kind of just precession in the rotating frame, when I go back to the lab frame, it's some very complicated evolution, but I can still understand its behavior very simply. And since it's happening in the rotating frame, it gets a name called Rabi oscillation. And Rabi oscillation is what I get when I drive the system close to resonance, and I see this flopping between excited thrust. Right. Okay, so that was the end of the reminder of basics. So before I go on, any questions on that part? Yes?
You mentioned before that you were saying if I take a Hamiltonian that changes time, I can get full control over my quantum state. What are you allowing us to play with there? Just the time, or?
You say, so the claim was, if I take, I guess I didn't make a very, very precise claim. So suppose I have two different unit vectors, n1 and n2.
Yep.
Let's let those be fixed. So I can, whatever it is, my system, I have just, it's fixed and allow me to control, I can apply either n1 or n2, and then I could choose how long I apply h1 and how long I apply h2. That's enough. So if n1 and n2 are given to me, and they're not parallel, even if it's a tiny angle between them, and probably I may need to alternate these many times. It's not that I just do it once each. And with that, I can go anywhere I want. Okay. Good question, thanks.
My question is, if you compare these quantum results with something what you can found within the Landau-Lipschitz equation, what will be connection between them? I can explain the motivation of my question. If you have some Hamiltonian of this kind,
this kind here, or this Hamiltonian, or different one?
Anyone linearly spin. You can apply a spin coherence state.
Yeah.
And for spin coherence states, this is a theory. But everything what you can find in quantum mechanics can be found as well in Landau-Lipschitz. Is it the case?
Is it the case that anything for a coherent state can be found, or that any quantum spin problem is the
Quantum
same.
spin problem for spin 1/2.
For spin 1/2. For spin 1/2, from the point of view of dynamics of coherent states, I think the answer is yes. Now, when it comes to measurements, of course not, because spin 1/2, if I measure something, I get projection on only two possible answers.
Spin 1/2.
Yeah.
It's exact description of spin 1/2 is spin coherence.
Exactly. Yeah. I agree.
And so, the theorem which was formulated by Periodically concerning spin coherent state and spin 1/2 and Landau-Lewis equation should be applied here.
Yeah. So in terms of dynamics of coherent states, there's no difference. What I want to say is, if you make, say, single-shot measurements, then spin 1/2 is very different from a classical spin. If you only look at averages, I think then you won't see the difference. And if you go beyond spin 1/2, of course, there's squeezing and other things, non-classical.
If you are going beyond spin 1/2, spin coherent state is good enough. You have to apply more general coherence. As you do, as you free and so on. But, okay.
Yeah, I think the question really is that in quantum getting to a harmonic oscillator, we have Ehrenfest theory. And you can go from quantum variables to expectation values, and they will both identical to classical mechanics.
Yeah.
And the same will happen here, because we don't have to go from coherent state to expectation value and policies.
Yeah.
They will both in the same
I agree.
There's no difference.
I agree, yes. But there is a difference when you measure. If you have single-shot measurements, then you can tell the difference between quantum and classical. That was the statement. So averages, yes, it's the same, but individual measurement outcomes will be different between quantum and classical. Anybody else? Yeah, we can discuss after. Still. Okay, so we gave two very simple examples of when we could understand evolution in a driven system, but obviously the world is much more rich than that, and we need to go beyond it. So we need to go somehow beyond this simple rotating field kind of driving. And the technical tool that's useful for thinking about this and going there is this Fouquet theory. So we'll spend some time going through that. It's a little bit technical, but it's useful. And since this is a school lecture, it's allowed to be more technical than a usual talk, I'll claim. So let's try it, see how it goes. Yeah, I wish I had a blackboard, but, well, I'll try to go slowly, and just slow me down if it's too fast. Because, with slides it's difficult to maintain the right speed. So a second ago we talked about this rotating field, and there was some magic, which was that by going to a rotating frame, actually this driven problem actually just became equivalent to a static one. But in almost all cases, that's not possible. So generically, there is no simple unitary transformation I can make such that when I'm done, I'll have a new Hamiltonian which doesn't depend on time anymore. And we need to understand what to do. So even almost the most natural thing you can think of, let me just apply, instead of this weird complex exponential sitting here, I just put cosine. Okay, so this is a perfectly fine and natural time-dependent Hamiltonian to write. For example, if I have, in NMR, this is what's done all the time. I have spin in a magnetic field, and I just apply an AC field along one direction. That's cosine. That's exactly this. And I could try going to a rotating frame, but it's not going to help that much. I'll still have some time dependence. Okay, so now I want to use this to start a more general discussion about periodically driven systems. So what are we talking about here? First of all, we've already been doing it, but we're talking about systems where the Hamiltonian depends on time. Now, if we want to do some kind of quantum control, in principle, we may allow any time dependence we want. We can change parameters in any crazy way, but there's not very much we can do on a theoretical level to describe anything general about that case, and get any behavior I want. So we'll restrict our attention to periodic driving, where the Hamiltonian repeats itself for some period, which hopefully will be called capital T throughout this talk. I think it is. I don't think I ever switched that convention. So capital T is always the driving period. It's never going to be temperature. Temperature does not appear in this talk. Right. Okay, so we know a lot about how to study systems with Hamiltonians that don't depend on time. We diagonalize Hamiltonians, look at ground states, look at the spectrum, etc. But for a time-dependent Hamiltonian, there's no such thing as a ground state. There isn't really even such a thing as an eigenstate. I could instantaneously diagonalize H at every moment of time and look at some kind of instantaneous eigenstates. But unless I'm driving very slowly, so the system is adiabatic, those eigenstates are meaningless. They're not useful for understanding the dynamics. So just trying to diagonalize H of t at each t doesn't help me. I need to do something else. And fortunately, when we talk about a periodically varying Hamiltonian, there is something we can do. We can actually recover some aspect of the familiar concept of a spectrum and eigenstates that we have for a non-driven system. And basically it's related to the fact that, you know, we have a conservation law of something, or we have a symmetry. So usually if H is constant, we have this continuous time translation symmetry, and that's where energy conservation comes from. In this case, we have a discrete time translation symmetry, and because of that, there's some kind of conservation, and it's conservation of quasi-energy, which I'll explain now. So the analogy I want to make, because this is something that's probably more familiar, is first about particle moving in a crystal, and then we'll relate it back to gravity. So recall that if I have a particle moving in a constant potential, I have a continuous translation symmetry of space, and because of that I have a conservation law of momentum. Now, if I think about an electron moving in a crystal, if I didn't know anything about quantum mechanics, I would say there's no way this particle would ever make it through. It's crazy. It's going over all kinds of rough potential fluctuations, and there's no sense in which its momentum should be conserved. In fact, that was one of the early problems that physicists were thinking about before quantum mechanics was developed. Why is there such a thing as a metal? Electrons should be scattering all the time. But in fact, once we learned that electrons are waves, we can understand that, in fact, the discrete translation symmetry of the lattice means that there is still something conserved. It's not the original momentum, but it's this crystal momentum. So here, for this case, I can say there's some unitary operator, translation operator, which commutes with the Hamiltonian. It's just because the potential is periodic, and simultaneously diagonalize H and this translation operator. And since it's unitary, its eigenvalues are unit modulus complex numbers, which I can parameterize like this. And it's very suggestive. This K, it looks like momentum, because if I would translate by a distance A, usually I would use the momentum operator P to do it. Here I have this eigenvalue K. It's almost the same as momentum, but it's not quite. And the reason is that actually the eigenvalue of this finite discrete translation is this unit modulus complex number. And so whatever this eigenvalue, or piece of eigenvalue, this parameter K is that I stick there, I could have picked a different value where I change K by 2 pi over A times an integer, and I would get the same value, same eigenvalue of this T back. So that's actually the reason why we have a Brillouin zone in a crystal. So I have a discrete translation symmetry, so I have this complex exponential for my eigenvalue, and therefore this K parameter must live in a circle, not just the whole real line like momentum did in free space. Okay, so this is how I get from having a real number for momentum in a system with continuous symmetry to a parameter K which lives on a circle, a Brillouin zone, when I have a discrete translation symmetry. Now, essentially, the same idea applies in the time domain when I have a periodically driven system. So here now, I have this evolution operator. This is the time-ordered exponential we described earlier, which propagates the system forward in time through one complete period of the driving. So the Hamiltonian will be the same in this first time 0 to t, and the next period t to 2t. And I can think about diagonalizing it. Right? So this, basically what is it? This u is a discrete map for my evolution. If I have a state at 0, I can propagate forward through time t by applying this unitary operator. And if I want to get to time 2t, I apply the same operator again and again. So really, in discrete time, it acts the same way as the constant Hamiltonian does in a system which is not being driven. It's the same operator which operates on each time step. And why do we spend so much time diagonalizing Hamiltonians for static systems? The point is that if I expand the evolution in the basis of its eigenvectors, the evolution is very simple. I just get some phases. So the same thing will apply here. If I would expand evolution in the eigenbasis of this U, it'll be very simple. Each eigenstate will just pick up some phase, which is here, and what do I want to say? Well, that's it. It'll be very simple on that basis. Right, so I can look for such eigenstates of U, and again, they're eigenvalues of the unit modulus complex numbers, and I can parameterize them in a very suggestive way, because if this Hamiltonian didn't depend on time, then I would just pick up a phase, e to the minus I energy times time. Right? That's the way an eigenstate's phase evolves in a non-driven system. So here, I've written the eigenvalue of the time evolution operator on its eigenstate, e to the minus I epsilon t. That defines what is this epsilon. And so it looks very similar to energy, but just like K, which appeared for a crystal a second ago, looked like momentum but wasn't quite momentum, this quantity here, which looks like energy, isn't quite energy. We call it quasi-energy. And you see that if I would add 2 pi over t times any integer, I would get the same eigenvalue back. So the point is that in a periodically driven system, this quantity, which is kind of like energy, this quasi-energy, it has a Brillouin zone itself. It lives in a circle. And it's only well defined up to integer multiples of this 2 pi over t. Now 2 pi over t is just omega, that's the angular frequency of the driving. And there's a physical meaning to this, right? I mean, it sounds kind of mysterious. What does it mean for energy to be defined mod, omega? It means that the system can absorb and emit quanta, h bar omega, from the driving field. I start with some energy, it can absorb 1 photon, 2 photons, it could emit 1, and all these different energies are coupled to each other through the driving, but only in integer numbers of photons. It can't absorb half a photon. So that's sort of the physical meaning of this condition. Right. So now to try to actually find, yeah.
About the physical meaning, I didn't quite understand, because, for example, this T can be some period of external energy, totally classical, and why should it be the case that any particle of such a field would be absorbed into such parts?
Right, it's an interesting question, and later also I want to make an analogy between classical driving and sort of this quantized field picture. So from the classical field point of view, actually we'll see how it comes out. I don't have a good explanation for why the system should know that there's such a thing as quantization of photons in the driving field. But sort of from Fourier analysis of the Schrödinger equation, we'll see that somehow frequencies can only shift by integer multiples of this frequency. But also there's an alternative viewpoint from view of quantized fields where obviously there's h bar omega. If there's a deeper connection, there may be a deeper connection, but I actually don't have a simple answer ready for either. Any other questions? Right, okay, so basically now we can try to analyze and find what are these. Here I said there are eigenstates of this evolution operator, and we need to find out how to find them. Right, we need to solve something. And the way to do it is to use the Fouquet theorem, which it pains me to say it this way, but it's sort of useful sometimes for people. This is Bloch's theorem in time. Now it's painful to say it because Fouquet lived long before Bloch. So Bloch's theorem should be called Fouquet's theorem.
Space.
Huh?
Fouquet's theorem of space.
Yeah, Fouquet was just some French mathematician studying differential equations. I don't even know what his motivation was. So the variables are probably x and y. So it's a very general theorem, and it shows up all over physics in different guises. But since probably everybody in this room is familiar with Bloch's theorem, but maybe not everybody heard of Fouquet's theorem before, it's useful to remind you that basically, Fouquet theorem in space is Bloch's theorem, and Bloch's theorem in time is Fouquet's theorem from our purpose. So the connection that you should note is that, what does this Fouquet theorem say? It says I take my time-dependent Schrodinger equation with this time-varying Hamiltonian, and there will be a complete set of solutions, meaning they form an orthonormal basis of the Hilbert space, which take the form of some kind of phase which grows linearly in time. This is like the plane wave part of your Bloch state in the crystal, and then a periodic part, like your Bloch wave function, which repeats itself along with the driving field. Okay, so now we just need to find what are these, it's sort of an ansatz for a wave function. We need to find out, what are the, how can I describe this periodic part phi, and how do I get this eigenvalue epsilon? And the useful thing, one useful thing, is that since this phi is periodic, I know that I can decompose it in a discrete sum of Fourier components with all integer multiples of the driving frequency omega, and I don't need any fractional harmonics, because I can only take harmonics which would reproduce this periodicity. Okay? And I can express it within some particular basis if I like. But the good thing is now I have some sort of ansatz for the wave function, and if I just know what is this list of Fourier coefficients which sits here, then I'll have a complete description of my state. So that's our goal now, is sort of what equation do these Fourier harmonics satisfy so that I can solve it and find out what are my solutions. Okay, so we just plug in to the Schrodinger equation. We take this state with this Fourier decomposition, plug it into the Schrodinger equation. All I've done is take time derivative right now. This is the left-hand side of the Schrodinger equation. Take time derivative. I either act it on this e to the I epsilon t and e to the I m omega t, which gives me this piece here. Right, so that's what I get from time derivative. The right-hand side of the Schrodinger equation is just h times psi, and this is psi. So the first thing I can do is cancel out those base factors in front.
Short question. Can
Yes.
you remind what was alpha?
Alpha is just some time-independent basis for the system. Good. Any other question? We should go slow. I mean, it's doing equations with slides is not the greatest, I know, but we should go through it. So please just ask everything that doesn't make sense. So now the other step is basically just to project this onto a given state in a given Fourier harmonic, and then we'll find out what equation is satisfied. So to project, first I need to take a bra of this other state beta, whatever it is, come in from the left on both sides. So I'm equating this line with this one, and multiply by some harmonic. I want the m prime component to come out, so I should just multiply by e to the I m prime omega t and integrate. And now I'll isolate one harmonic component from each side. So what comes out when I do that is, essentially what I'm doing is Fourier transforming the Schrodinger equation. That's what I'm doing. And what I get is something magical. So I get that this, now phi, this phi now is a shorthand for the list of all, I just take all of these Fourier coefficients that I had to describe my state and just stack them up into a big vector. And amazingly enough, this giant vector of Fourier coefficients satisfies something that looks like a time-independent Schrodinger equation. So this is just an eigenvalue equation with some Hermitian matrix sitting here, and then this really giant vector of Fourier harmonics there. And now this so-called Fouquet Hamiltonian, which sits there, is basically the Fourier transform of the Hamiltonian with some extra piece sitting here. So it almost sounds too good to be true. Right? We started, we had a time-dependent problem, we don't know how to solve quantum evolution with a time-dependent Hamiltonian, and now I said, well, let's just plug in this particular form of solution, and suddenly we're back to solving a time-independent Schrodinger equation, which presumably we do know how to do. So we must have paid a price, and the price that we paid is that, originally we had some Hilbert space. I didn't tell you how big it was, but let's say that this, alpha here, which is our basis, there are n. Suppose there was a two-level system, there are two different values of alpha. If it's an n-level system, there's n of them. But now we have a list of Fourier coefficients, and for each harmonic m, I have n of those. But then this m actually runs from minus infinity to infinity. So I've traded essentially a finite dimensional diagonalization problem for an infinite dimensional one. Okay, so now you can say, did I win or did I not win? First I had a time-dependent problem, I didn't know how to solve it. I have an infinite dimensional matrix, I still don't know how to solve it. But it turns out that from a practical point of view, we've actually gained a lot. So first of all, there's some very specific structure here. So let's take a look at this matrix, and then I'll show you that, in fact, we never have to, in many cases, in practice, we don't have to worry about the fact that it's infinite dimensional. We can truncate it and use some finite dimensional version of it and get very close to an exact result. So first of all, the structure of this matrix. It's particularly simple if I have a driving which contains a single frequency, one harmonic. Okay, so you can do this with any kind of driving field you want, which is periodic. The simplest case is single harmonic. So first of all, it's a giant matrix, but it has a block structure. And on the diagonal, I have blocks which are essentially the DC part, zero frequency part of the Hamiltonian, just copied over and over again, shifted by integer multiples of omega. So you see it's h0, h0 plus omega, could be 2 omega, 3 omega as I go up. So this is diagonal blocks. And then the off-diagonal blocks are just related to the coupling. So this term here with frequency in it, you can see if we think about the Fourier transform that we did a second ago, any term which had e to the I omega t can change my frequency by 1, my harmonic by 1. So that's what jumps me between the blocks. Okay, so is this structure okay? Good. Right, so there's another question which comes up, should come up. Nobody asked it. Maybe somebody should have. I told you we started with a system which was n-dimensional. Okay? Now we have this infinite dimensional matrix, and I'm going to diagonalize it, and I'm going to get infinitely many eigenvalues and eigenvectors. But my problem is still living in an n-dimensional Hilbert space. So I have a problem. What are all these extra solutions that I found? Right? It should bother you. If it doesn't, it should bother you now. What does it mean? Why do I have so many solutions? Well, the fact is that they're not all independent of each other. In fact, if I had an n-dimensional problem when I started, I'll only find n distinct physical solutions when I go back to writing the actual state of the system. So to show you, here's this sort of Fouquet-Ansatz wave function with quasi-energy epsilon and some harmonic expansion. Now you see, I can just grab n harmonics from here and move them out there. So if I would shift my quasi-energy by some integer times omega, I can compensate by also shifting all my harmonics here by the same number n. And this is, I didn't do anything. This is exactly the same state that I started with, but it has a different eigenvalue from this problem. This would be epsilon plus. So the point is that there's a huge sort of degeneracy of solutions. I solved this infinite dimensional matrix, but there's only n solutions I need to find. And then there's many other ones which are just copies of the original. It's basically like looking in a fundamental Brillouin zone, or crystal. Right? I have crystal momentum. I could look in some extended zone scheme where I have k and then in the next zone and the next zone, but actually somehow I'm just getting copies repeated over and over again of the same solutions. Okay, so that's an important point to keep in mind. Now, what's really useful about this matrix is this block structure that I mentioned actually has some intuitive picture that you can think about. So a block tridiagonal matrix basically describes the nearest neighbor type binding problem, right? So if I think of each of these blocks as a site, then in some kind of imaginary fictitious lattice in my mind, then this delta is a hopping which takes me from one lattice site to the next. So I can relate this, basically this strange eigenvalue problem that's going to give me the solution to the driven system to some kind of hopping on an effective one-dimensional lattice. And this lattice is a little bit funny because it's a lattice with a linear potential on it. I see that the energy of each of these effective sites changes by omega each time I take a step forward. So this Floquet diagonalization problem is closely related to, it's called the Wannier-Stark problem, finding what are the eigenstates of a particle on a lattice in a linear potential, say in a constant electric field. And here there's some useful picture to keep in mind which tells you that, in fact, the solutions are localized in space, in the space of this lattice. And this goes under different names. One is this Wannier-Stark problem. The other is Bloch oscillation. If I have an electron in a band and I apply an electric field, one way to view it is that the momentum of this particle will shift linearly in time, and it'll just move around on this dispersion curve. And velocity, which is the slope, will spend the same amount of time being negative as positive, and the particle will oscillate in space. That's a Bloch oscillation. And now if you want to ask, how far can this particle, what region can it explore? Basically, this band that it has, so if I would ignore the linear potential, right? There's some kinetic energy of this particle coming from its hopping. So there's a bandwidth which is 2 delta. That's the maximum amount of kinetic energy I can give or take from this particle. So if I start it off in some location, it can explore the region of this lattice, changing its potential energy until it has no more kinetic energy to give or take. So that means there are some kind of classical or semi-classical turning points, and the particle can't go beyond it. So the reason I'm going through all this is to tell you that in terms of this matrix, we actually from this picture understand, hopefully, that the eigenstates are localized in this M direction. I have some state which is localized starting around M equals 0. It'll explore some region of M's close to 0, but at some point it'll stop. It'll have some exponential or even faster decaying tails. And that's what allows me to truncate this matrix. If I just need to find solutions, somehow centered around here, if I go out far enough, past these turning points, and then just chop off the matrix, I won't really mess up my answer very much. And so that's why, from a practical point of view, this Floquet business is quite useful for calculating things. So one exercise is a bit more challenging one, but it's actually a very interesting problem, and the answer itself is quite interesting. It's actually this. I needed the answer to this for some problem I was working on in research, and it just so happened that in class I was teaching this thing, so I gave a bonus problem, and a student found the answer to this question, and actually didn't believe it at first, because it's kind of a funny answer. But it turned out that this decay is even faster than exponential. I didn't expect that, but it is. And so you can do some kind of WKB type analysis to find that. So it's a fun exercise to do if you have some time. Right, so now let's try to use this to understand some example. Actually, how's the time?
5 minutes.
5 minutes?
Plus 5. If you really need it.
That's fine. Okay, so we should use this for something before we get cut off, right? So we already talked about this rotating field problem. We know the answer, we understand it very well. That's a great place to start checking if we understand this formalism here. We should understand how does that map. So if I take the rotating field example that we already discussed and map it into this Floquet language, what I find is there are disconnected 2x2 blocks in this giant matrix, which allow me just to simply diagonalize. So even in this case, even though I have this infinite dimensional matrix, I can diagonalize it. It's so simple. And that's basically relating to the fact that the problem is almost trivial. I can go to the rotating frame and solve it. But now that we have this formalism at our disposal, we can go beyond the rotating field case and say what happens if I add so-called counter-rotating terms, the terms I would get from, say, cosine driving instead of this rotating field, they will appear, you know, in some other positions in this matrix and couple different blocks. And because of that, it's no longer a trivial problem to solve, but now understanding this, you know, structure, it gives me some way, either perturbatively in an appropriate limit, or you know, numerically if I have to, at least to understand what happens. And also there's sort of a new physical phenomenon that appears. So for just the rotating field, all I have is so-called single photon resonance. I can only excite the system if my driving field has the same frequency as the energy splitting. But once I have other terms which couple here, I can have multi-photon resonances. Suppose I drive at half the frequency of the splitting. If my amplitude is big enough, I can still excite the system. And you'll find that if you go, you know, play with this matrix, you can find that that's possible by including these other terms. In fact, you won't get a 2-photon resonance from this, you can get 3. So you have an exercise to understand which types of multi-photon processes would be allowed by this type of driving, and there'll be some that you miss, so what would you have to change about the driving in order to get the rest? Okay, so that's actually something that will sort of check your understanding of what's going on. Okay, so in the last 2 minutes, I'll just tell you, you know, some sort of modern application of this. So suppose now, instead of, you've been talking a lot about two-level systems. So if I have, let's say, a system with 2 bands, or a particle and a lattice, and I have, say, 2 bands, for each k, I basically have a 2-level system. And if I only apply uniform fields, I never couple different k's. So this is basically an extension of what we've been talking about. So now suppose I have this system, you know, 2-band system, and I start driving on top of it. So there are many proposals, which we can discuss, for manipulating band structure and topology of bands and so forth in such systems through time-dependent driving. And the basic idea, just like, you know, we showed at the very beginning, that's why I went through those simple examples, was, you know, suppose I go here, if I would imagine this rotating field, suppose I can apply that to this crystal, whatever that means. Okay, in the rotating frame, essentially I can take, you know, one branch of states and shift it up, and near these resonant points, the driving will couple the 2 bands and can open new gaps and can change the form of the bands. Okay, we can understand that. And so one application also, which has been very popular, and where there are even some experiments trying to probe it, is this can be used to open gaps at the Dirac points of either graphene or the surface of a topological insulator by shining circularly polarized light onto the sample. So there are actually many references about that. This part came here from, there's a simple limit to take where the frequency is very high compared to, say, the bandwidth system. And you can understand this gap. There's an even simpler version, which is your last exercise you can use to understand it. Either you can solve this problem with a continuous field, or it's enough, actually, if you want to understand, and here the Hamiltonian involves only sigma x and sigma y. To open a gap, I need sigma z. So you can ask, in what way does shining circularly polarized light give me a sigma z? The simplest way that I know of to sort of convince yourself that it'll work is take this circularly polarized field and just break it into 4 steps that appear in a sequence, again connecting back to what we discussed before, 1, 2, 3, 4. And this will involve sigma x, sigma y, sigma x, sigma y. And when you look at the commutators, you see sigma z will appear for you. Okay, so that's one, you know, final example. I suggest we work out, and I'll leave it there. Please, if you have further questions, ask now or later. I'll be around and happy to discuss.
So what happens when you put temperature in this?
When I put temperature in.
How do I do statistics on this?
Okay, so that's an excellent question. So the point is that in a periodically driven system, for many reasons, there's no simple statistical mechanics or thermodynamics like we usually have. We have energy coming in and out of the system. One particular issue that should be in mind is that I mentioned that this energy-like variable, this quasi-energy, actually lives in a circle. Therefore, it's not even clear which state is above and which state is below. I could shift my definition, and suddenly the ground state would look like excited state. So what happens in practice I mean, I assume when you ask that question, what happens to temperature, I think what you mean somehow is, suppose I connect to a bath and let it thermalize, and then what would the distribution be, say, on these full K states? First question is there a distribution just in terms of full K states, or is this a good basis even for describing the steady state? Sometimes yes, sometimes no. We can discuss when that is. But in general, whereas in usual stat mech, the form of the bath doesn't matter, the way that it's coupled to the system doesn't matter, as long as there's coupling and as long as it's a large reservoir. Here, everything matters. So the specific form of the coupling between the system and the bath is actually important to the steady state you get. So there's no universal answer. But we've studied specific cases, others have studied it, so we can discuss more later.
Let me ask you a quick question in relation to this.
Yeah.
For me, the most painful aspect in this whole business is dissipation. I understand dynamics well, depending on the situation, but is there some strategy or some clever insights or some special cases or classes of cases when dissipation could be somehow mitigated?
Yeah.
Can you say something clever about it? Let's say that's a question.
I'm not going to say that I say something clever. That's kind of weird.
Can somebody say something clever about it?
Yeah. So first of all, here I was mostly focusing on few level systems. Now, if we're talking about many body system where dissipation starts.
Like environment again.
Either environment or many body system. There's essentially three approaches. First of all, many body system just wants to heat up, so it somehow fight.
Right. And you want to somehow.
How do we fight it, right? So one is okay. We can add a bath, and then we and other people have worked on understanding what type of coupling to the bath would you need to stabilize a nice state versus a totally crazy one.
Yeah.
So there's some ideas there. Second is in many body localized systems. It's a big active area right now. Somehow dissipation, or if there's a bath, MBL is not so clearly defined, maybe it doesn't exist. But for an isolated system, which is many body localized, this heating actually is suppressed.
Okay, but that's a very exotic, I would say.
It's exotic.
Case.
The third is that there is something called prethermalization. So there are regimes such as very high frequency driving, where the driving frequency, let's say the energy of a single photon in the driving field is much bigger than any local energy scale in the system. So we have to make many excitations to absorb one photon.
Sure.
Then my heating is
kind of off-resonant.
Right. So off-resonant for any kind of dissipation in the system. And there's sort of a different version of it, which I'll actually talk about in my conference talk, which happens at low frequency driving, something related with different people.
Okay.
I can hear him.
Does Q theorem simplify in the didactic limit when driving frequency is small compared to
Well, okay. Depends what simplify means. So if you would really take, so one way to think about taking adiabatic limit here would be just throw away omega on the diagonal. I can do that, and then in fact this sort of fake tight binding problem that I mentioned, if I Fourier transform it, it actually gives me back the instantaneous Hamiltonian and tells me the Floquet states are the instantaneous eigenstates.
Does it give Periodically? It's a good question. So if I take all the way just to setting omega 0, I won't get Berry phase. I'll just get average energy. But maybe there's some way to perturbatively add the omega back in, which is a good question. I don't know.
Because you need single photon interband processes to get the Berry phase and all that, I suppose, I'm guessing.
Yeah, I mean, so actually, what I'll talk about on Monday is actually partially thinking about. So there is something useful that does come out of the adiabatic limit. So Berry phase does get picked up there. I haven't thought about it starting from omega equals 0 and putting it back in. But it is the case that Berry phase is picked up if we go to low frequencies here. And quasi-energy spectrum that you get has a very special structure, which involves both the dynamical and Berry phases. So sort of adiabatic pumps can be understood in that way. Yep.
Can this approach be used to solve systems with non-radiative pathways for radiation or excitation?
So what you mean that I'm driving it and there's some additional dissipation
non-radiative way to lose the energy.
Right, so I think that's related to Yaroslav's question about dissipation. I mean, so this, strictly speaking, what I described, well, it depends what you include in your Hamiltonian. If you would include everything, then it's there. Now, you know, if it'll be useful in that case is another question. So if you try to do this, say, for the system and the whole environment, so that each one of these blocks actually is a whole many-body Hilbert space, the problem is very messy. There's not too much you can say in that case.
But what about including something like a phonon subsystem?
Right, so if it's weakly coupled, then you can develop some kind of Floquet master equation and try to solve it. There are various approaches to solving sort of open system plus periodic driving. Probably that's what you would want to do in this case.
Any questions? You mentioned that now when you have this matrix, you then have to restrict the number of solutions. Is there a way when you look on the simple case of two-level system to see how this restriction has to work out? And just generally, maybe you can talk just a little bit more about how you restrict them.
So there's two versions of restricting. So one version of restricting is that we have too many solutions. So in fact, all we need to do is pick two of them. So here, I mean, you can see, was this argument clear why I have too many?
Yes, but how do you do it in practice then?
Right, so in practice, all you need to do is basically define one Brillouin zone of energy, quasi-energy. So you just pick, say, the interval from 0 to h bar omega, and you're actually guaranteed that there'll be exactly two solutions which fall in that interval. And those are your two independent solutions, and you can pick those and ignore the rest. So basically, the solutions are repeated every zone, h bar omega, and within each zone, I have exactly the number of solutions which are independent. No?
I'll have
Okay, may I just finish saying the second part was I mentioned this truncation related to the fact that the solutions are localized in this harmonic space. And to do that safely, you kind of have to solve the problem first, or use this kind of argument to understand how many harmonics I should keep before I truncate. And then you should only take solutions from the very center of this band that you kept, because the ones near the edge where you truncated will be messed up. But in the center, it's safe.
On 010, which is what are relevant energies for Gibbs factors?
Okay, so that question, I guess, is related to the earlier one. And I guess what I should say is that in general, the steady state of the system, when it's coupled to a thermal bath, will not be described by Gibbs factors at all. So there's no e to the minus beta quasi-energy which shows up. Only in very, very specific conditions, which we can discuss after if you're interested, will you get something like a Gibbs state. Otherwise, you'll have some probabilities and possibly some coherences between Floquet states which describe steady state. So there's no simple rule I can give because it doesn't exist.
I mean, to truncate your matrix for Hamiltonian, you should study your distribution and distribution.
Right. So there's different. There's a truncation of Hilbert space. So if we start, here we're describing some, well, wherever, I don't know where I'm talking about it. Here, let's say here. This H, which is here, say I start with a finite dimensional matrix, meaning I've already truncated my Hilbert space of the problem to some, n levels. And I don't want any occupation out of that subspace of my full Hilbert space of the universe. Now, if I have guaranteed for myself, say because I have a bunch of levels and then a huge gap before any other ones, if I've guaranteed I'll only stay within those levels, then this whole description is okay. But I can't tell you anything general about occupation among those levels which are down there while I'm driving. That becomes very sensitive to the coupling to the back, form of everything, form of driving, etc. So there would be, say, occupation here, nothing in excited states of the Hilbert space, but within this low energy, original subspace, distribution can be very complicated and non-universal.
This index M, does it mark any real eigenenergy or?
Yeah, so to make this a well-defined problem, it should say, define some, I had original system, any real physical system actually has an infinite dimensional Hilbert space. It's living out in the universe. I somehow, there's some real energy scale that I start with, which is large, and I say that I never populate any levels above this real energy scale. Now I've restricted myself to some finite number of levels, and everything that I said throughout this talk was about what's happening in this finite number of levels, given that I never excite out of that subspace.
Could you please return to the matrix? Where is a strength of oscillator hidden? What determines at what speed the system will do this transition, except from the frequency difference and the strength of the external field?
Wait, those are the only two parameters that matter. So which extra parameters?
There is a third one, I think, or there should be. The one which would determine the properties of the material. For example, different materials would react differently to the same intensity and the same frequency, even if they.
So this matrix element V here is actually, it's the matrix element specific to this system. So I had, if I measure my intensity of applied electric field in volts per meter, I have to convert that through some coupling constants to get this. So it's already inside this V.
But it's from transformation of external driving force, right?
Yeah, so I apply, some AC electric field, and then that turns into some matrix element between states. That's all inside this V.
Is there a contribution from the form of original potential?
What do you mean original potential?
For example, if we have an atom, we have potential from other electrons which don't interact, in this example, with external field. And those determine how likely is electron to come to other level.
Right, so those, this external potential is what determines the eigenstates of the subspace I'm talking about, and this V is just some matrix element between those states. So
sorry, I just understood answer to my own question. It goes into H0 coefficient, which is not present on this slide, but it was on previous. So it goes into other constant contributions. So it goes with a constant external field.
Yeah, it should be both in the DC part and in the matrix elements. It's that's what describes everything.
Thank you very much for the talk, and I probably have a dumb question. So do you need to have some weak coupling between the bands, initially, or it's your rotating field that provides a sort of coupling between the bands?
So bands, now you're talking about this sort of example at the end?
Yeah, when you pre-put it,
yes. So initially, bands are already diagonalized, so there shouldn't be any coupling between them in that sense when I started. Now, when I apply this driving field, it's actually the strength of the driving which provides the coupling eventually to open up a new mini-gap between them. So it's really the driving strength which is going to do it.
So it's a nonlinear system?
Why nonlinear? The gap will be proportional to driving strength. It's linear.
Thank you.
Just a quick, crazy question. wonder if it's maybe possible, I wonder if there's any discussion about introducing thermodynamic effects somehow by mixing real and imaginary time, or maybe with some kind of mixed, real imaginary time. Is there anything in that sense that could, in some models at least, capture some thermodynamic aspects, or something that came out or was totally insane? Do you think about that?
I mean, there is a fairly good characterization of which conditions are needed to get something like thermodynamics, some equilibrium distributions. I'm not sure if anyone tried in that particular language or picture, but then outside of those conditions, it's not universal.
The driving is we go slow again. We know if there's no driving, we just work in the imaginary time, and everything is periodic from 0 to beta.
Yeah,
and then at least if you're not driving too strongly, that some leftover of that view might still be there. Maybe there's some kind of mixed, some kind of perturbative onset of this blockade bands on top of imaginary time consideration. And of course, I'm just
it's speculative.
speculating.
We can speculate, but
so nothing of that sort is like really fruitful.
Yeah, I mean, nothing that I know of.
So really no more time, so only from the young people. Sorry. Oh, okay.
Young at heart.
Anyway, I'm looking at this picture and wondering, does it make any sense to even think about some kind of dynamical, topological insulator behavior if I manage to open some gap where the bands cross up there? Like I have band inversion.
Yeah, exactly. So that was exactly the motivation behind this. So you can create a band inversion precisely in that way. So you start with non-inverted bands, and well, the picture's a little bit complicated, but these new bands here, after diagonalizing, have a band inversion. I've switched the original valence and conduction band here, and I would have a Chern number and edge states and all that.
You can prove it.
Yep.
So pressing questions from the junior participants. Otherwise,
we here have a case. We here have a case of weak coupling. If there are any prediction, what will happen when we have a case of strong coupling between the bands?
For this example again, or
yeah.
So in principle, the Fouquet theory, which described, is not a weak coupling. Doesn't depend on weak coupling for anything. So you can solve this problem even for a strong coupling. It's more complicated to do it, but again, you'll get some effective bands which come out. There can be additional sort of phase transitions. I shouldn't call it phase, but transitions where gaps open and close as a function of driving strength, not just frequency. This is an interesting problem to explore. And there have been some studies of it, but there's many questions.
One last pressing question. Oh, okay. Also, still semi-young.
So one comment about this adiabatic limit. So if the frequency is really small, that doesn't mean we can put omega goes to 0. It has to be compared to some other energy scale. So for example, many people in this audience work on pumping by microwaves. So microwave is some gigahertz frequency, and that's much more than Fermi energy. So like in that case, if I take this Fouquet theory and apply to pumping, let's say because memorization processes by that frequency, what I really see is that I need plus minus 10 photons or 10 blocks in your picture there to include to actually get the physical observables which do not change after that, roughly that number. So for this ratio, Fermi energy is 1 electron volt, and I'm running a precession by a few gigahertz. So the reason for that is that when I look at the observable, I have to add these blocks and see how my observable saturates eventually. So in other words, like having a high frequency looks simpler, which is what topological people do, because they do the Magnus expansion and they see that Hamiltonian gets corrected by 1 over omega. And then the higher the frequency, the smaller number of corrections I have to take into account. So the adiabatic limit is actually more complicated in Fouquet picture. for a really small frequency, you have to go to increasing a larger number of blocks.
Yeah,
so the question is really, the Fouquet is non-perturbative, both in frequency and in the strength of the perturbation. And the final result is non-perturbative, but it's classical. So you're considering this driving field to be classical.
Classical in terms of the driving field, yeah.
Yeah, so in quantum optics, when they do the same thing, they find Fouquet states, then a posteriori they can dress those states by switching to quantized electromagnetic field.
Yeah.
So like, is there any non-trivial effect in this community that has been considered that would come out by considering really many body photons interacting with electrons via diagrams that is not going to be taken into account simply by this kind of classical averaging picture?
Okay, it's a good question.
If the laser field is zero,
unless there is a quick answer, maybe a little bit. It's a
Yeah,
good question maybe for discussion.
Let's just discuss it. I think, yeah, it's
okay.
Probably out of time.
All right, so let's move on. Let's thank Mark.